Hemostasis is the process that stops bleeding at the site of an injury while maintaining blood in a fluid state within the vascular system. This complex process involves a series of well-orchestrated steps to ensure that blood loss is minimized and the integrity of the circulatory system is preserved. Primary hemostasis begins when platelets come into contact with exposed collagen, microfilaments, and the basement membrane of endothelial tissue. As small blood vessels constrict, platelets adhere to the exposed tissue. This action triggers the release of ADP and ATP, which promote platelet aggregation and act as energy sources. Additionally, thromboxane A is synthesized from arachidonic acid, further promoting activation, release, and aggregation of platelets. As platelets start to aggregate, they release more ADP, ATP, and serotonin, a substance that promotes vasoconstriction. Eventually, platelet receptor sites are exposed, allowing the binding of coagulation proteins from secondary hemostasis, such as fibrinogen binding at the glycoprotein IEB3A receptor. The primary goal of secondary hemostasis is to generate sufficient thrombin to convert fibrinogen into a fibrin clot. This stage involves the activation of intrinsic, extrinsic, and common coagulation pathway factors. The fibrin clot includes both the platelet plug formed during primary hemostasis and the fibrin formed in secondary hemostasis. The intrinsic pathway is activated when coagulation proteins are exposed to subendothelial collagen. This pathway includes factors such as taurine, Hagman, Serotonin, plasma thromboplastin antecedent, prekallikrein Fletcher, HMWK Fitzgerald, nonine, plasma thromboplastin component Christmas factor, and SATE, antihemophiliac. The extrinsic pathway, which is the dominant in vivo pathway, starts with the release of tissue factor from injured blood vessel endothelial cells and subendothelium. Tissue factor is found in most tissues, organs, and large blood vessels, and this pathway includes factor VII, stable factor. The common pathway begins with the activation of factor X by either the extrinsic or intrinsic pathway. It includes factors X, Stewart-Prower, V, proacceleratin label factor, 2, prothrombin, and I, fibrinogen. There are also alternative pathways that link the extrinsic, intrinsic, and common pathways. Additional synonyms to be aware of include tissue factor, 3, calcium, IV, fibrin stabilizing factor, 13E, and ristostatin cofactor, von Willebrand factor. Coagulation factors, also known as enzyme precursors or zymogens, are found in the plasma. They are accompanied by nonenzymatic cofactors and calcium. Zymogens are substrates that have no biological activity until they are converted by enzymes into active forms known as serine proteases. The zymogens include factors 2, 7, 9, 10, 11, 12, and prekallikrein. The serine proteases, on the other hand, are factors 2A, 7A, 9A, 10A, 11A, 12A, and kallikrein. Cofactors assist in the activation of zymogens and include factors 5, 8, tissue factor, and high molecular weight kininogen, or HMWK. In its active form, factor 13 is a transglutaminase. Fibrinogen is unique as it is the only substrate in the cascade that does not become an activated enzyme. The coagulation groups include the contact group and the prothrombin group. The contact group consists of prekallikrein, HMWK, and factors 11 and 12. These are produced in the liver and require contact with a foreign surface for activation, such as collagen in vivo or kaolin in vitro. The functions of the contact group include the reciprocal activation of factors 12 and prekallikrein, with HMWK acting as a cofactor in this process. All members of this group play a role in intrinsic coagulation activation. Additionally, factors 12A, kallikrein, and HMWK are involved in the inflammatory response, intrinsic fibrinolytic activation, kinin formation, and activation of the complement system. The prothrombin group comprises factors 2, 7, 9, and 10, all of which are produced in the liver. Vitamin K is essential for the synthesis of functional factors, with calcium binding sites necessary for binding to phospholipid surfaces, also known as PF3. Causes for the synthesis of non-functional factors include vitamin K deficiency, or the use of antibiotics that kill the intestinal bacterial flora responsible for vitamin K synthesis. Oral anticoagulants such as warfarin interfere with the metabolism of vitamin K, acting as vitamin K antagonists.